Hi everyone, I'm Yuze. My project is to estimate the relative depth map from the smartphone focus depth using only classical method, meaning no depth sensor or no learning-based model. So now I'm going to talk about the motivation and challenges to this project. So the input, as I mentioned, is the mobile focus depth captured by sweeping the focus setting on a phone. So the basic depth from focus idea is simple. So for each pixel, the frame where it's the sharpest give a focal index, and we treat that index as a relative depth. So however, when using the idea on a mobile stack, this brings two major issues. The first, the lens bracing changes magnification across the sweep. So frames are misregistered and the sharpness is compared at the wrong pixel. And second, many regions have those weak or ambiguous focal responses, especially in those low texture areas or highlights, which makes per pixel arcmax unstable. The right side does show an example. We see that those circle areas shows those different shadow shape, demonstrating lens breathing does exist. So here's a full pipeline. We start from the focal stack taken while sweeping the focus. We need to first align the frames, and after this, on a line stack, we compute a sharpness score in each frame, which tells how in focus each pixel is. And third, instead of picking the best frame independently per pixel, we encourage enforcing those spatial consistency. So the neighboring pixels prefers those similar focus indices, which produce a cleaner focus label map and an all-in-focus image. And finally, we normalize the focus label into a relative depth map, and we smooth mainly in uncertain regions using a confidence measure based on how separate the best and the second best sharpness responses are. So next is alignment stage. I use a two-stage strategy. The first, a global affine alignment using the ECC, which corrects the dominant breathing, induced zoom and translation between those consecutive frames. Then I run a fast dense optical flow method, the DIS, to refine the remaining local misalignment, especially near those edges and those like texture regions. And finally, I apply a backward warping to resample each frame into the same reference coordinate system. And I output an aligned grayscale gap for those like sharpness scoring and then aligned color stack for the all-in focus composition. So these are some of the results on the same thing after alignment. So those frames are all aligned to frame 0. And the first column is the original, the second one is the line, and the difference image demonstrate that alignments are done correctly. So after alignment, each pixel corresponds to the same point and across the stack. So we can finally compare those like focus responses consistently. So for each aligned frame, I compute a simple sharpness score using the image gradient, and then spatially smooth it to reduce those noise in those low texture regions. So I formulate those focus selected as like a multi-label MRF, and the unary term preferred those frames with higher sharpness, and the pairwise term encourages those neighboring pixels to choose similar focus indices. So once we have the spatial consistent focus label map, converting it to the depths is pretty straightforward. So however, because those labels are discrete, the depth map often shows the banding and the piecewise constant regions, especially where the focus response is weak. So to address this, I compute a simple confidence score at each pixel, which is the difference between the best and the second best sharpness responses across the stack. So during the refinements, those high confidence pixels keep their original depths, and the low confidence regions are smoothed using those neighboring reliable estimation. So these are some of the example results of the on-focus images. So from the top, we can see that the dense bracing causes those final image looks blurry, and the pixels are not aligned. So with the proper alignment method mentioned before, we can see that the final alignment images looks clean. So here are the depth results on two things. On the left is the baseline, and the middle one is the confidence guided refinement, and the right is the absolute difference. So for the second row, this is more of a failure case because the result is not as stable. So the large wall region is much further than the like object, and in that area, the focus responses is weak and doesn't show like a clear peak across the stack. So to wrap up, I will summarize the main limitation and takeaways. So first, the system produces those relative depths from those focus indices. So it does not recover those metric depths or absolute scales. And second, when the scene contains those like large distance or low texture regions, the focus response can be weak and the focus curve may not have a clear peak, which makes the label-based depths unreliable. And in conclusion, this is like a fully classical and learning-free depths from focus pipeline for mobile focus stack. These are the references to this class, and thank you guys.